Determine whether the following series converges or diverges. Sum from 1 to infinity to the root of n plus 1 all over n squared plus 2. The presence of those plus signs separating the terms is an indication that ratio, maybe even root, won't work well. You don't want to integrate this thing. It's not alternating, but it's an indication that some comparison would work. Now, the fact that they're both plus signs is an indication that direct comparison wouldn't work. If you're adding to numerator and adding to denominator, it's going to be hard to make that inequality work out. And so, with that in mind, oh wait, one check, I'm sorry. The limit's definitely 0. The denominator grows faster than the numerator, so that's not helpful either. So we're going to try the limit comparison test. And we go get our bn by dropping off the plus 1 and the plus 2. Drop those guys off, and we end up with n over n squared, but underneath the root. Inside, that simplifies to 1 over n, but it's underneath the a root. So it's 1 over n to the half. Make sure you know what your b sub n series does. The series on this guy would diverge. It's a p series. Ultimately, if we can show that the limit of an over bn is a constant, then they will behave alike. So we put the a sub n in the numerator, b sub n in the denominator, and we divide and see what happens as n gets big. Dividing by n to the half is the same thing as multiplying by root n. And if you have this root here, you can make it one large root and then basically incorporate the n up in the exponent and give yourself n squared plus n. Ultimately, what happens there is that you can bring the limit inside of the root. Degree of the numerator equals degree of the denominator. Ratio of the coefficients 1. Square root of 1. We get 1. This limit is 1, which would be bad for the ratio and the root test, but okay for the limit test. It tells you that they behave alike. You went out and got a divergent series. They behave alike, so the series that you were given also diverges.